In previous lecture on angular momentum operator in quantum mechanics, we have seen the expression for the operators associated with the components of orbital angular momentum in Cartesian coordinates. Now today we are going to find the operators corresponding to the components of orbital angular momentum or orbital angular momentum in spherical polar coordinates. Actually, I have said in the earlier lecture that the expression for operator in spherical polar coordinates for orbital angular momentum is very important to find the eigenvalue and eigenfunction of this operator. So let us see how we can obtain the expression for the operators associated with the components of orbital angular momentum components in spherical polar coordinates. For this, let us see this figure. You have seen these situations earlier in several times. Actually, I have shown here the three Cartesian coordinate axes, that is x-axis, y-axis and z-axis. And there is a point P in a space whose position vector relative to the origin is equal to r, as you can see in this figure. In fact, the Cartesian coordinates or the space coordinates of this point P are x, y, z, and the spherical polar coordinates of the same point P are r, theta, phi, as I have mentioned it here. As you know, if we want to relate the Cartesian coordinates of this point P with the spherical polar coordinates r, theta, phi, then we have to mix a particular geometry. For this, you have to draw a perpendicular PQ on the xy plane. As you can see, actually this line PQ is normal to the xy plane. And when you join this point Q to the origin O, then this OQ is actually the projection or the component of this position vector r in xy plane. So you can say that this OQ is simply rxy. This is projection of vector r in xy plane. And then we draw a line QA, which I have shown by this dotted line, parallel to y-axis, and so it will be perpendicular to this x-axis. So this angle is pi by 2. Although this angle does not appear equal to pi by 2, but in 3 dimension this angle is actually pi by 2. And then this projection OA is equal to x. So I have mentioned here OA is equal to x. In this is actually the x coordinate of this point P. And similarly, when you will draw a line QB parallel to this x-axis, that will be perpendicular to the y-axis, and this projection OB is equal to y. This is y coordinate of this point P. And again, when you draw a line PC parallel to OQ, then this PC is perpendicular to z-axis, and so this angle at C is pi by 2, and the projection OC is equal to z. Now the spherical polar coordinate, you know this OP is the first coordinate, that is r, that is radial coordinate, and this angle POZ, this is theta. This is another spherical polar coordinate of point P. And the angle made by the projection of vector r in xy plane, that is this rxy or OQ with x-axis, this angle is phi. This is the third coordinate. Now you have definitely seen in the lecture on classical mechanics that how we can transform the Cartesian coordinates into the spherical polar coordinates and spherical polar coordinates into the Cartesian coordinates. I have not actually make here all the calculations. You have seen this earlier. So I have written here some of the important results which we have already seen in our course on mathematical physics. So you know these are the transformation equations. If you know the spherical polar coordinates are theta phi, then by using these transformation equations you can find the Cartesian coordinates x, y, z as the equation says. X equal to r sine theta cos phi, y equal to r sine theta sin phi, and z equal to r cos theta. You know it. Similarly, if we transform the orthonormal basis x hat, y hat, z hat, actually this x hat has been written instead of I, y hat instead of j, and z hat instead of k. So these are actually the unit vectors, you can say, in Cartesian coordinate systems, a system directed along the x-axis, y-axis, and z-axis. And similarly, in a spherical polar coordinates, we consider the orthonormal basis like this: r hat, theta hat, phi hat. Actually, r hat, theta hat, phi hat, all these three are the unit vectors in the increasing direction of r, increasing direction of theta and phi. And in similar manner, these orthonormal basis vectors in Cartesian coordinate and spherical polar coordinates are also related to one another. And you must remember it that x hat is equal to r hat sine theta cos phi plus theta hat cos theta cos phi minus phi hat sine phi. Similarly, y hat is equal to r hat sine theta sine phi plus theta hat cos theta sine phi plus phi hat cos phi, and z hat is equal to r hat cos theta minus theta hat sine theta. To find the expression for operators associated with the components of orbital angular momentum, you must remember these transformation equations. But for its derivation, we also need two more operators in spherical polar coordinates. All these things I have discussed already in chapter curvilinear coordinates in the course on mathematical physics, and you have seen these things. Actually, the gradient operator in spherical polar coordinates is denoted by this symbol del, and this is defined like this. This is the definition of gradient operator in spherical polar coordinates, and you have seen the proof of this result in your course on mathematical physics in the chapter curvilinear coordinates. So if you have not watched that video, you must watch my video on this gradient in a spherical polar coordinate system in curvilinear coordinate system chapter. So you can see here, del is r hat del del r plus theta hat 1 over r del del theta plus phi hat 1 over r sine theta del del phi. This is expression for gradient operator del in a spherical polar coordinate system. And you have also learnt in curvilinear coordinate system the expression for the Laplacian operator, or simply Laplacian, in a spherical polar coordinate system. You have seen that Laplacian is denoted by this symbol del square, and del square is nothing, this is simply del dot del, and in a spherical polar coordinate system it is defined like this: 1 over r square del del r, r square del del r, plus 1 over r square sine theta del del theta sine theta del del theta, plus 1 over r square sine square theta del 2 by del phi square. So here I have mentioned these important results which you have learnt in the earlier lectures in mathematical physics, but the use of all these results will be needed here to obtain the expression for the operators corresponding to the components of orbital angular momentum in a spherical polar coordinate system. So now remembering these results, now we will see how we can obtain the angular momentum operator and the operators corresponding to its components in a spherical polar coordinate system. So let us see it. You know, the orbital angular momentum operator will be defined in a manner which we have learned actually in the previous lecture. So orbital angular momentum operator orbital angular momentum operator. Actually, in the previous lecture, I have denoted this orbital angular momentum operator by the symbol L hat. And this is defined like this. This is R hat cross P hat. And you know, this R hat is the operator corresponding to the position vector and P hat is the operator corresponding to the linear momentum vector. Actually, for convenience here, I am dropping this sign of this hat for the operator. And instead of that, we will simply write the operator by the symbol capital letter. It means you can write this expression like this, L equal to, but here remember this L is the operator associated with the orbital angular momentum. And for R hat, now I am writing capital R. And for P, a small p hat, now I am writing capital P. So when we will write the symbol by capital letter, you must think that these are not physical quantities or observable, but operators. So, this is just for your convenience. You will see in calculation, such type of symbol will be more convenient. So instead of R hat, now I am writing capital R, and for small p hat, I am now writing capital P. Now in a spherical polar coordinate, you know this operator capital R is written like this. This is in fact R times R hat. Remember, this R hat is the unit vector, that is the radial unit vector, not operator, remember it. And this linear momentum operator, you know, this linear momentum operator is minus IH bar del. So you can say this orbital angular momentum operator. I am again telling you that this is not angular momentum, but this is angular momentum operator. This is equal to minus IH bar times R and R hat cross del. Now, to obtain the expression for orbital angular momentum operator in a spherical polar coordinate system, what you will do? You can see actually here there is del operator. So if your aim is to find the expression for orbital angular momentum operator in a spherical polar coordinate system, you must write here the expression for this gradient del in a spherical polar coordinate system. So I have mentioned it here. You can see this equation 3. I have already mentioned that this gradient operator in a spherical polar coordinate is defined like this. So write here this expression. So we will write R hat del R plus theta hat 1 over R del del theta plus phi hat 1 over r sine theta del del phi. This is the expression for gradient del. Now let us take the vector product of this r hat, this is just a unit vector, with all the three terms inside this square bracket. So this is minus I h bar r. Now see, here in first term the unit vector is r hat, so there will be r hat cross r hat, and you know r hat cross r hat, what will be this? This will be 0. Cross product of similar vector is 0. So this first term becomes 0. Now in second term there is theta hat, so there will be r hat cross theta hat, and you know r hat cross theta hat will be equal to phi hat. Just like I cross j equal to k, similarly r hat cross theta hat will be equal to phi hat. So this is plus phi hat 1 over r del del theta, del del theta. And in third term there is phi hat, and you know r hat cross phi hat, this will be minus theta hat. So here there will be minus sign, so minus theta hat 1 over r sine theta del del phi, del del phi. Now when we will multiply by this factor r to the terms inside the square bracket, this r and this r will cancel out, you can see. Therefore you can say that the orbital angular momentum operator L, this is equal to minus I h bar phi hat del del theta minus theta hat 1 over sine theta del del phi. So remember, although I have derived this result, but you should remember it too, because in the problem or in other theories we will directly write this expression for the orbital angular momentum operator. So this is your first result for the orbital angular momentum operator, and you can see this L is equal to minus I h bar times phi hat del del theta minus theta hat 1 over sine theta del del phi. Now after getting this result for the orbital angular momentum vector operator, it is very easy to find the operators corresponding to the components of orbital angular momentum vector. As you know, if you want to find the component of a vector in a particular direction, what you do? Let us consider that there is any vector, let us say A, and you have to find the component of this vector in this direction, let us say in this direction. This is an arbitrary direction. The simple technique is what? We simply take the scalar product of this vector A with the unit vector directed along this direction, in the direction along which we have to find its component. So if let us say u hat is the unit vector in this direction, then this u hat dot A, this gives actually the component or projection of this vector A along this direction. This concept will be utilized to find the operators associated with the components of angular momentum vector. So now the operators corresponding to components of L are, let us say, for x component we now write the operator Lx hat, which now I am writing only Lx. In the first lecture I have written it Lx hat. Now for convenience I am dropping this sign of hat, so I am just writing Lx, but that Lx is the operator corresponding to the x component of orbital angular momentum vector. And according to this concept, as you know, if you want to find the projection or component of a vector in any direction, you have to take simply the scalar product of that vector with the unit vector in that direction. So if you want to find Lx, what you will do? We will take the unit vector x hat, which is in x direction, and we will take the scalar product of this unit vector with the orbital angular momentum operator L. So x hat dot L will give the operator Lx hat or simply Lx. Now to find this Lx in a spherical polar coordinate system, we will put the expression for this x hat in a spherical polar coordinates. So I have mentioned it earlier, you can see it here, that this x hat, which is first orthonormal basis in Cartesian coordinate system, that is related to the spherical polar coordinates like this. This is r hat sine theta cos phi plus theta has cos theta cos phi minus phi hat sine phi. So we will use this expression in that equation. So let us put it here. So instead of this x hat, what you will write? We will write this will be r hat, not x hat. I am writing here instead of x hat the expression in spherical polar coordinates. So see here, the expression for x hat is what? This is r hat sine theta cos phi plus theta hat cos theta cos phi and minus phi hat sine phi, phi hat sine phi. And we have to take its scalar product with L. But we have obtained in this equation A1 the expression for this operator L. This is minus I h bar phi hat del del theta minus theta hat 1 over sine theta del del phi. So put it here. This will be in fact minus I h bar, see the expression, phi hat del del theta, phi hat del del theta, and minus theta hat over sine theta del del phi, del del phi. Now we will simplify this result, taking the results of a scalar product of orthogonal unit vectors in your mind. you can simplify this result easily. Now see this minus I h bar. Let us write it first of all. Minus I h bar. Now see, in first term there is r hat, and here in the first term there is in fact phi hat. R hat dot phi hat. This will be 0. And again we will take, in fact I am writing here r hat dot phi hat. This will be equal to r hat dot theta hat, and all these will be equal to 0. In a scalar product, the scalar product of dissimilar unit vectors, orthogonal unit vectors, will be 0. So there will be no term corresponding to this r hat. Now take the scalar product with this second term. Theta hat dot phi hat, that will be also equal to 0. Theta hat dot phi hat, that will be also 0. But theta hat dot theta hat, that will be 1. So we will take the scalar product of this second term with this term. So theta hat dot theta hat, that will be equal to 1, This is equal to 1. So this will be what? This will be actually minus cos theta over sin theta into cos phi del phi. Now take the scalar product with this last term, phi hat sin phi. Phi hat dot phi hat, that will be 1. So this will be again minus phi hat dot phi hat 1. So this is simply sin phi del theta. And again phi hat dot theta hat, this will be 0. So last term will be 0. Now see, if we will introduce this minus sign inside the bracket, both of the terms will become plus. So you can now see this operator Lx is equal to what? This is I h bar and sin phi del theta. I have written here the second term first, and plus cos theta over sin theta, that will be cot theta times cos phi del phi. And this is actually the expression for the operator Lx or Lx hat. This is another important operator, in a spherical polar coordinates. Now, in similar manner, you can find the operators Ly and Lz in a spherical polar coordinates. So now, tell me, if you want to find the operator Ly hat, which is now writing here simply Ly, not Ly hat. I am writing now it simply Ly. So I have written here a sign of equivalence. And to get this operator, what you will do? We will take the scalar product of this orthonormal basis y hat with L. Again, we will put the expression for y hat, which you have seen here earlier in this expression for y hat, and then we will substitute the expression for operator L, and after that we will simply take the scalar product, as you have simplified the result in this case. So I am not here writing all those things. This is just a homework for you. You should try, write the expression for y, write the expression for L, and then take simply the scalar product. then you will get the expression for this operator Ly. So I am dropping here those calculations, but you should try it yourself. Then you will get this Ly operator will be equal to IH bar minus cos phi del theta plus cot theta sin phi del phi. This is the another important operator. In similar manner, you can also find the operator Lz. Now you can easily say what will be this operator. For this, we will take the scalar product of z hat with L. Again, we will substitute the expression for z hat and L hat, and after simplification, you will get Lz equal to minus IH bar del phi. Actually, this is the simplest expression for the operator. Simplest expression. Although this expression is simplest, that is the operator Lz has the simplest expression, but this is the most important operator when we will actually find the eigenvalue and eigenfunction of operator. We will find the eigenvalue and eigenfunction of this Lz, and calculation will be very easy. So you must remember it, Lz equal to minus IH bar del phi. Now after getting the operators corresponding to the components of the orbital angular momentum vector, now we are going to first of all find the expression for the square of this operator. So the expression for L square is, this operator L square can be defined like this. This is L dot L. And we have already obtained the expression for operator L, which is defined here in equation A1. So substitute this expression for L, and then you will get the operator L square. So you can see, as here there is minus IH bar as a common factor. So when we will take L dot L, this minus IH bar and minus IH bar will be multiplied, and that will be what? That will be simply minus H bar square. Minus H bar square. So minus H bar square. And again the operator L operator, in fact we should not try to use this expression, but it will be easier to write this expression. You can see it here. The angular momentum operator L is equal to minus IH bar R times R hat dot del. Let us start with this expression for L to get the expression for L square. That will be more easier. So I am writing it here. So what will be this? You can see this is minus IH bar minus IH bar. What is the next? Minus IH bar R hat cross del. Minus IH bar R times, sorry, this is R hat, not vector R. there will be r hat cross del, and this is expression for L, and again dot L. So this will be again minus I h bar r hat cross del. Now see, this minus and this minus will become plus, I square will be again minus 1, and h bar square r square. So this will be minus h bar square r square, minus h bar square r square, and this r hat cross del a dot r hat cross del. So right here r hat cross del dot r hat cross del. Now see this expression. In fact, this expression r hat cross del dot r hat cross del can be simplified by the formula for the scalar product of four vectors. A scalar product of four vectors. Do you know the formula for a scalar product of four vectors? For a scalar product of four vectors. You have studied it in vector analysis. This is A cross B dot C cross D. Can you say what is this formula? In fact, in determinant form, we define like this. This is A dot C, A dot D, and B dot C, B dot D. In this form, you can remember this expression, and you can see this will be A dot C times B dot D minus A dot D times B dot C. And here in our expression you can see, instead of A cross B dot C cross D, there is R hat cross del dot R hat cross del. So using this formula you can simplify it. So therefore R hat cross del dot R hat cross del. What will be this? You can write it in this determinant form. This will be R hat dot R hat and R hat dot del, and again del dot R hat and del dot del. Now simplify it to some extent. You can see this will be R hat dot R hat. This is 1. You know R hat dot R hat is 1. So 1 into del dot del. This is del square. And minus del dot R times R dot del. So you can see this will be simply del square minus del, actually this is hat, not vector sign, hat. Now this is del dot r hat. R hat, you know, this is radial unit vector. This is unit vector in the radial direction. So r hat is defined like this. This is actually vector r and divided by mod of vector r, you know, and times again this r hat will be defined by vector r divided by mod of vector r dot del. Now you can see this expression can be written as del square minus. Now this mod of r times mod of r, this will be 1 by r square, you can easily say. And for this del operator in a spherical polar coordinate, we will write here del r. And this r dot r, this will be r square. And for this del, again we will write del r. So this product r cross del dot r cross del is equal to this much. This is del square minus 1 over r square del r square. This is actually r square. Just erase it. This is what? This is r square. So now you can use this result here to obtain the expression for the operator L square. So when we will use in this expression here, what will be L square, you can easily see. So therefore the operator L square will be equal to what? This is minus h bar square r square times, see the expression, this is this much. So this is del square minus 1 over r square del r square del r. Now in a spherical polar coordinate system, you have seen the expression for this Laplacian operator. This is also an important result, or you can say an important expression for this operator. This is A4. This is also very important. You will see the use of this form of operator for L square in later section. Now in a spherical polar coordinate system, in a spherical polar coordinates, you know, this Laplacian operator is equal to what? This is 1 over r square del r square del r plus 1 over r square sin theta del theta sin theta del theta, and plus 1 over r square sin square theta and del 2 by del phi square. This is actually expression for Laplacian del square. So you can see when we will substitute this expression of Laplacian in equation A4, this second term will cancel out. Or in other words, you can say that when you will bring this first term in LHS, then that will be simply del square minus 1 over r square del r square del r. And that will be equal to the sum of these two second term. So using this in equation A4, what you will get? Therefore, you will get L square equal to L square equal to and remember this R square will also cancel out, so this will be minus h bar square 1 over sine theta del theta sine theta del theta plus 1 over sine square theta del 2 by del phi square. This is the most important operator of quantum mechanics. Actually, you will find the use of this operator at various places when you will discuss the problem of rigid rotator, the problem of hydrogen atom. You will always find this expression there. In fact, in case of rotational spectra, you will find the application of this operator. So this is very important, so must remember it. Now, in terms of this L square operator, we can also express the Laplacian operator. That is also a very useful form of the operator of the Laplacian operator. So now we are going to find the expression for Laplacian operator in terms of this L square operator. And that can be done by the use of this equation A4. You can see from equation A4 we can easily find what will be del square in terms of this L square. That is also a useful form of Laplacian. So from A4 you can see, from this equation you can see del square minus this much will be minus L square over h bar square R square. So we can write del square minus 1 over R square del R R square del R. This is equal to minus L square by h bar square R square minus L square by h square by h bar square R square. Yes. Now, in del square you can write this is 1 over R square del R R square del R and minus L square over h square h bar square R square. And this is also a very important form of the operator Laplacian. And this form of Laplacian will be used also at various places. When actually we discuss the problem of hydrogen atom, you will see that this form of Laplacian is very useful there. So I will suggest you, although you have derived this result, but you should also try to remember it, because whenever we find its application we have to write this expression directly. So also try to remember this expression. So you can see in this lecture we have seen the angular momentum operator, it's the operator associated with its square, with its components, and Laplacian in spherical polar coordinates. So after this getting this expression, we will try to find the eigenvalue and eigenfunction of the components Lx, Ly, and Lz, and also for the operator L square. So wait for the second video when we will meet together again and discuss the eigenvalue and eigenfunction of the operator, first of all Lz, and after that L square and L.